Anybody have questions for me? Robbie.
Number 11 on 2.5.
2.5, number 11. Look, somebody doesn't want to spend their entire weekend doing their homework, right? Hey, look, it's not like I'm trolling you. I'm just backing Robbie up for being already into 2.5. So 11 says, suppose that f and g are continuous functions such that g of 2 equals 6, and the limit as x approaches 2 of 3 f of x plus f of x times g of x is equal to 36. And we're looking for f of 2, and we know that g of 2 was 6. Howdy. How are you, Luke?
I'm good.
Taylor.
I'll be back, maybe.
Okay.
I might just stay gone.
Oh, I don't blame you.
All
All right.
To start my day with.
So, since this is continuous, that means that all these limits need to exist, right? By the definition of continuity. So I can do all my little limit tricks on this and break this up and write it as this, right? Everybody's cool with that? And since this is continuous, I know that g of x is going to, or the limit as x approaches 2 of g of x is the same as just g of 2. I'll see you in a bit. Does that feel okay? And then these are like terms, so I can just add those together. Okay with that? Divide both sides by 9. And again, since this is continuous, the limit as x approaches 2 of f of x is just equal to f of x. So it's 4. Or I'm sorry, f of 2 is 4. Sorry. Does that feel okay? You guys buy all that? So continuity did a lot of heavy lifting there and allowing me to like just substitute things in and move things around. And it's quite a powerful property if you have continuous functions. Mia. 2.3, number 62. Sure. Oh yeah, this is just a bugger. I think you'll probably have, yeah. I think you'll probably have to do multiplying by the conjugate. Maybe, well, let's see. I actually saw this one. I went, oh, that's going to be a cute one, and I didn't actually work it out. So you're going to get to see me fumble through this in real time. Okay, just says to evaluate this. And obviously, we can see that if I do a direct substitution, you get something over 0, and that's no bueno, right? In fact, you get 0 over 0, which is very much like indeterminate. Like, what can I do with that? Nothing. So I would probably think the first thing to start with would be to multiply by the conjugate. Well, because the zero, if I can get rid of the zero in the denominator, a zero on the top is fine if I do the direct substitution. But if I get rid of the top, if I have a zero in the denominator, it's still like a kind of a problem, right? To do a direct substitution. So that would be my reasoning for wanting to do that. So this is going to be then the square root of 3 minus x times 6 minus x, and then minus 2 square roots 3 minus x, plus a square root 6 minus x minus 2. And then the denominator, since that's a difference of 2 squares, I'm just going to get a squared minus b squared. Okay. So if we do that, that's not going to help us out a whole lot because I'm just going to end up with 2 minus 1 down there, right? Or 2 minus x, which is still a big problem. You guys agree? Well, let's take another look at this. Should we keep going and see if there's some other tricky thing that can shake out up top, although it doesn't particularly look like it? Let's see. So what I'm going to do up top is I'm going to do a factor by grouping, and I'm going to group those two terms together and then those two terms together. In the yellows, I see I have a factor root of 6 minus x, and in the greens, I have a negative 2. So I'm just going to factor that out and see if I can, if that's going to, no, that'll just give me back what I started. I can see it now already. Well, that's disappointing. Well, let's see what suggestion they make before I go start. The next thing I would think to try would be to multiply the conjugate with the numerator, since that what we tried there just obviously didn't work. But before I go through all that trouble, let's Mr. Kulik just cheat a little bit. Ah, very clever. Okay. Yeah. Okay. You guys ready? So that didn't work, right? So I'm just going to erase what we did there. You guys are okay with doing that? So I'm going to now multiply by both conjugates.
Oh, that should not be legal.
I don't know.
So when I do that, I'm going to actually just write it below since it's I kind of want to look at everything. So the way I'm going to write this is I'm going to do that part and then down here I'm going to multiply these together. So that's going to give me 2 minus x, and that's going to give me 2 minus x. And then, let's see, I don't want to reduce those, I don't think, because that'll just put me right back in the same boat. So let's FOIL that stuff out. I'll just have the reciprocal of what I had before, which would still give me a 0 over 0 when I do my direct substitution. Huh? Oh, yeah. Yeah, thank you, before I got going. Excellent. Yes. That solves our problem. Because we're adding now instead of subtracting. So when I do my direct substitution, 3 minus 2 plus 1 is 2. And then root 6 minus 2 plus 2 is 4. So I get a half. Serge.
Would you give us a problem with that calculator test?
I mean, probably not. I haven't written the test yet. But that's, I mean, it's number 62 for a reason. Right? It's pretty deep down in that problem set. But it's nice to see that, like, okay, this looks like an obvious multiply by the conjugate problem. I tried multiplying by the conjugate, didn't work. What else could I do? Try both conjugates. See how that goes. In this case, that did it. Got rid of the problematic part, which was nice. Yeah, are you? Yeah, it was fun to work through that together. Depending on your definition of fun, I suppose. Mackenzie. From section 2.3, number 36. Sure. So this says, use the squeeze theorem to show this limit is 0. Okay, and then it says illustrate the function, or by graphing the functions of f, g, and h on the same screen. So, what is the key piece of this that I'm going to use to build my functions for f and h? Sine, yeah. So I'm going to start with sine x, because I know sine x is bounded between -1 and +1. Everybody's cool with that? And I know the only things coming out of sine can be between -1 and +1. So certainly this is still bounded between. You guys agree with that? Doesn't matter what I take the sine of. The biggest thing I can get is 1, and the smallest thing I can get is -1. Doesn't matter what else is inside there. Everybody cool? And then I'm going to multiply both sides then by that radical x cubed plus x squared. Okay with that? So this is my f of x, this is my g of x, and this is my h of x as per the squeeze theorem. So I know that the limit as x approaches 0 of g of x is going to equal the limit as x approaches 0 of f of x, which should be the same as the limit as x approaches 0 of h of x. Everybody's okay with that? To do the limit as x approaches 0 of f of x, I'm just going to use a direct substitution on that. Should be easy to see that that's got to be 0. I'll write it this way. And same thing for the h of x. Should be easy to see that that's 0. So we're done. Probably in here I should have written by the squeeze theorem before I said that those limits are all equal. Does that feel okay, Mackenzie? Kind of. Here, let's look at the picture. So I have negative square root x cubed plus x squared. I have square root x cubed plus x squared times sine of pi over x. Then I have the positive and we'll graph that. That seems okay. I want to check my mode real quick. I am in radians. Okay. So I can't really see what's going on here very well, right? So I'm going to go zoom in real close. It looks like everything interesting is happening near the origin. So I'm just going to go from like -1 to +1. Let me make those steps by 1/10. So this is the first function. That's my f of x. Here's my g of x. And then here's my h of x. Notice f of x bounds g of x below, and h of x bounds g of x from above, and they are all meeting there at 0. That's kind of what the squeeze theorem is saying. So the limit of the upper and lower bounds being the same at 0, and if g's always in between them, g's got to have the same limit, right? Does that feel okay? Yeah. You know. Anybody else? Mackenzie? 32 from the same section. Just says to evaluate the limit if it exists. Oops, x squared. So obviously direct substitution is a problem, right? So we get 0 over 0. So what I'm going to do here, or what I'm looking at with this fraction inside a fractions thing, this is called a complex fraction. You could think about this two ways. You could think about this as your numerator, and then this as your denominator. And since that denominator just includes a single term, I can just multiply by the reciprocal of the denominator to get rid of the fractions inside of fractions, which feels like the easier thing to do. Is that okay with you, Mackenzie? Okay. Now I'm going to write that out front. like that. So far, so good? All right, so the stuff inside the parentheses then, going to find the common denominator. Cool? What would the common denominator be? X plus h squared times x squared, right? Everybody, you guys all agree with that? Okay. So I'd have x squared minus x plus h squared over x squared times x plus h squared after I make my common denominators and everything. You guys can see that? If you can't, I can spell it out for you a little bit more, but I think at this level that's okay to just say what I did and then write it. If not, you guys will tell me, right? You're not shy about stuff. You know me now. Some of you, it's been 3 years. Mm-hmm. Yeah, imagine for me.
Yeah.
Having to put up with you guys for 3 years.
Yes.
Ah ha ha.
Which year was like your longest?
For your teaching career, what year? Or like you just had a student where you're like, I just can't.
Oh, I don't know. It all blurs together.
This is probably a stupid
Mine
question. But what made it so you can take the denominator and just multiply it by the without rest of brackets? Like I did in the first step.
I made a common denominator and added the two fractions. Right, like I multiplied this by x squared over x squared, and this by x plus h squared over x plus h squared.
Oh, wait, you lost it, I'm sorry.
You're asking how I went from here to here, right?
No, from there to like there, which had.
There to there.
Yeah.
So from the original problem to the
Yeah.
first step, I multiplied by a reciprocal, right? We divided two fractions. So the yellow divided by the green, multiplied it by the reciprocal.
Okay, yeah,
Is that cool?
yeah.
Okay. If I go and I look down here now, Mackenzie, the x squareds cancel out. And then we have a common factor of h that can cancel. And that's what I needed because now I have no factor of h in my denominator. So when I do a direct substitution, I get negative 2x over x to the fourth, or negative 1 over x cubed. There's my answer. It looked really bad, but at the end of the day, you know, that's okay. Now, this is certainly something I think is an appropriate level to see on a test.
So then what about it?
What's up?
Why didn't it go
Why did it go away here? Because I did direct substitution. I plugged 0 in for all the h's.
Okay.
So that's why the limit disappeared. Does that feel good?
Yes.
Wait, I have a question.
Yeah, go ahead.
Is direct substitution when you just plug in what the limit is going to for that?
Right. So I took this and I put 0 in for h.
Okay. And
So-
you can do that from the beginning, but if it goes all to 0, then
If you get something in the indeterminate form like 0 over 0, that doesn't tell you anything.
okay.
That's why we had to do all this simplifying mumbo jumbo.
Fine if you get like 0 over 4.
Uh-huh. That's just 0.
Right.
That's okay. So there are, what are there? There's like 6 indeterminate forms. So if you get 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. These are all things that are indeterminate. Like you can't say they're not equal to infinity, they're not equal to 1, they're not equal to 0, they're not equal to whatever. They're like indeterminate. And to kind of illustrate to you why they're indeterminate, say you have like 0 over 0, right? The limit as x approaches 0 of x over x, well, that should be 1. But if I plugged it in directly, you get 0 over 0. If I have x squared over 0, well, that should give me 0, because the x's would reduce out after you reduced it. Here, again, 0 over 0 would become 1. Here, look at this one. If I plug in 49, I get 0 over 0. But if I do the reduce this, like you factor this as a difference of 2 squares and reduce, you get 14. So like 0 over 0, indeterminate could be a whole mess of things, right? Like in fact, you could create a limit where it could be any value. It would not be difficult to do that. In this example right here, that's exactly what they're doing, right? You pick any value of a, and that limit's going to equal a, even though it's direct substitution gives you 0 over 0. So those are the ones that you have to worry about, is when you do your direct substitution, you end up with one of these guys. 0 over 0 is the most common one you'd see. Mackenzie? Yeah, of course.
Would it be negative 4x?
Oh, yeah, thank you. The 2 should still be there. Thank you. Yep. Yep. No problem. Okay. What do you guys think? Ready to get a move on here then? Got a bunch of questions knocked out there. Overall, things are still going okay? Overall okay?
25 subject
Yeah.
it definitely does get harder.
All right. So we have a little bit left to cover in 2.5. There's one idea left that we need to talk about here, and it's a biggie. It's called the intermediate value theorem, or often we'll abbreviate that as IVT. And it says that suppose f is continuous on the closed interval from a to b. When I say closed interval, I mean the one with the brackets on the end. And let n be any number between f of a and f of b, where those two values are not equal, then there exists a number c that's in the open interval from a to b, such that f of c is equal to n. Let's draw a picture to illustrate what this is really saying, because although this sounds rather technical, it's like an incredible nodoi kind of thing. So let me draw a little picture here. So let's say that this value here is a, and this value here is b. I've drawn a continuous function here. So this value over here should be f of b, and this value down here should be f of a. Everybody agree with that? what the intermediate value theorem says is I can pick any number between f of a and f of b. So maybe there's my number n. If that's the case, I should be able to find some value c that evaluates out to that number, which of course you should, right? If you have a continuous function and that has outputs between two values, you should be able to pick a value in between those two outputs and find an x that goes to it, right? Of course you should. Everybody agree? Like, very obvious when you draw the picture and you think, like, what is this saying? Just saying that if I take some interval over which a function is continuous, and I look at like the maximum minimum value, or just actually what the function evaluates at the endpoints, if I pick a value in between those two outputs, there has to be something on that interval that maps to that value, right? Because you would have had to cross that y-coordinate somewhere going from A to B. You would have had to cross that y-coordinate because it's continuous. There's no way to like skip over that y value. Does that make sense to you guys? Now, could the function contain values of n that are outside of f of a and f of b? Yeah, certainly could, right? Imagine it did like that. Right? You could have values of y that are outside of f of a and f of b. That's okay. But every y value in between f of a and f of b is covered by some output from that function still. Does that feel okay to you guys? Relatively easy idea, right? Little technical in the wording, but pretty easy idea. So let's do an example of applying this now. Show that, let's just say the equation has a root between 1 and 2. So what are we going to do here? First, I'm going to observe that the function in question here is a polynomial. Everybody agree with that? And since it's a polynomial, what do I know about all polynomial functions? They're continuous over their entire domain, which is all real numbers. So certainly we're continuous on the closed interval from 1 to 2. Everybody good with that? Because that's the first thing in my theorem, right? I need f to be continuous. So my first step is going to be, I got to be continuous on the interval in question. Everybody solid there? Now I'm just going to do, maybe I'm going to call this guy f of x just for some notational ease. I'm going to do f of 1, which is 4 minus 6 plus 3 minus 2, which is negative 1. And then I'm going to do f of 2, which is 32 minus 24 plus 6 minus 2, which is equal to 12. Everybody still doing okay? And I know that let n equal 0, that f of 1 is less than n, which is less than f of 2. So by the intermediate value theorem, there exists an x in 1, 2 such that f of, let's say c, f of c is equal to 0. That backwards e is the mathematical shorthand for there exists. It's a common mathematical phrase. That's a common abbreviation, is that backwards letter e. You don't ever have to use it. I sometimes, like in this case, wrote it without it thinking because, I don't know, sometimes that's just what happens, right? Mia?
Do you put a 0 because like it said
Yeah, that's what a root means, right? Is that it's a solution to this equation equal to 0. So that's why I chose n to equal 0, because that was the output that we were looking for. Exactly right. You guys feel okay? That's the intermediate value theorem.
So it's like, what's the final answer?
Well, so the question said show that
Oh,
there's a root between. They didn't ask us to find the root, it just showed that it exists. So this is kind of like a proof kind of thing.
okay.
So I would, like I would treat it like a proof, and it's just like, I've done it. I've used the intermediate value theorem to show that I can find such an x.
Okay. Why did you choose 1 and 2?
Because the question said
Between 1 and 2, yeah.
between 1 and 2. So that's where the 1 and 2s are coming from.
Yeah.
Does that help to go by and color code it where like,
Yeah, I'm just like, let's. You wanted it to equal to 0 because at the top, it's like the whole equation is equal to 0.
mhm. That's why I chose n to be 0.
Right. But I don't know, maybe I'm just.
Go ahead. It's okay. Stumble your way through it. Ask your question.
What does everything else mean? Like the f of 1 is less than n is less than 2.
So if I look at the intermediate value theorem, it says that let n be a number between f of a and f of b. So that's what I've done here, is I found f of a, and I found f of b, and I picked an n in between them. Then, using the intermediate value theorem, I can conclude there is some number whose output gives me n.
Oh.
So that's how I got this last sentence here. So just following the, setting up the theorem and then using it to cross the finish line. Is that
Okay, yeah.
okay?
I understand. Thank you.
Good, no problem. So the 2.5 homework, if you're looking in the textbook, is on 125. And obviously this matches, I think, what I have up. Now, and this corresponds to the edition, the 7th edition, right? I think we all got that cleared up where we're all using the 7th edition now. Mr. Kulik posted the 8th edition mistakenly on the digital platform, but I think we're all good now. All right. 2.6 then. This is limits at infinity and horizontal asymptotes. Okay. So recall back to your Algebra 2 class. I know that's a long time ago. So remember we talked about rational functions. So maybe something like this, right? Was a general rational function. How would I find the different asymptotes for something like this? Okay, so to find the vertical asymptotes, I can take the denominator set equal to 0, right? Now in this case, that has no solution, so there's no vertical asymptote. How do I find the horizontal or oblique asymptote? There were 3 cases, right? We had to look at the degree of the numerator with the degree of the denominator, and that told us what to do. Now in this case, the degree of the numerator is 2, and the degree of the denominator is 2. When the degrees are equal, that horizontal asymptote is going to be the leading coefficient of the numerator, which is 1, over the leading coefficient of the denominator. That's 1. So if I have a horizontal asymptote where y equals 1, that would mean that the limit as x approaches negative infinity of f of x should be 1, and also the limit as x approaches positive infinity of f of x should be 1. So I used the asymptote rules from Algebra 2. So to find the other asymptotes, the non-vertical asymptotes, I have to look at the degrees of the numerator and denominator. In this case, the degrees were equal. They're both degree 2. In that situation, you'll have a horizontal asymptote where the numerator is going to be the leading coefficient of the numerator. So the 1 in front of the x squared. And the denominator will be the leading coefficient from the denominator. So again, the 1 in front of the x squared. Is that okay, Mackenzie?
Wait, did you say the leading coefficient will be from the denominator will be the leading coefficient of the numerator? Or did you say it will be of the denominator?
So yeah, everything matches. So like if that's the green one is the denominator and the blue one is the numerator. So it's the same match. Does that help to color code it so we can see what's going on? Okay. Right? So it appears that I can rewrite these horizontal asymptotes using these infinite limits, right? But what does that really mean? What does an infinite limit like that really mean? We haven't seen that before, where x is going towards negative or positive infinity like that. So let's give the technical definition. So f is a function defined on some interval. Let's say a to positive infinity. Then the limit as x approaches positive infinity of f of x is equal to L means that the values of f of x can be made arbitrarily close to L by requiring x to get sufficiently big. And we could say the same thing now about a negative infinity, right? But instead of the values of x getting sufficiently big, they'd have to get sufficiently small. So instead of writing a second definition, I'm just going to cheat and save myself a lot of words. Requiring, probably, is the word that I questioned. I should probably go and erase that and rewrite it, but I was in the middle of a thought and I didn't want to stop right there to do that. Was I right? That's what it was that we were having trouble reading. I don't blame you. Now, when you read this, was this sounding a lot like? L sounds a lot like a line the graph approaches but doesn't ever touch. Sounds a lot like an asymptote, right? And because L is a y value, this would be like a horizontal asymptote. So again, we can now recast our definition for a horizontal asymptote. We say the line y equals L is called a horizontal asymptote of f of x if either the limit as x approaches negative infinity of f of x is equal to L, or the limit as x approaches positive infinity of f of x is equal to L. Yes, of course. So let's look at an example here. Let's say we have y equals tan inverse of x. So we'll check both directions there. And to evaluate this limit, I am going to use, I think what do you want to do? A table? That probably makes the most sense, right? What do you think, guys? Because we obviously can't do direct substitution on this, since the x value that you'd be subbing in is an infinity. That's a problem. You could graph it also, I suppose, if you wanted to. Let's do that, I guess. Doesn't hurt to do that. So I'm going to graph this using zoom trig. So it certainly looks asymptotic there, right? Looks like it's flattening out. That's a fun word to say. You'll impress your friends if you can work that into a sentence. But picking that value, I don't know, it's somewhere between -1 and -2 and somewhere in between +1 and +2. But if I don't know what it is, this isn't entirely super useful to me because it doesn't look like it's going down to an integer value. So let's use the table option. So I think I put that in Y4. So I'm just going to do the -infinity way first. So I'm just going to kind of keep picking smaller and smaller values of x and seeing if that's going to settle down to like a specific value. What do you guys think? Are you starting to recognize that number yet? Yeah. What is that? -0.57? It's -π/2 is what that looks like to me. Why did Mr. Kulik even think that this was going to be in terms of pi?
He's just a genius.
No, it's an inverse trig function, right? It should be outputting an angle measure in radians.
I made it go.
Yeah, like how do you just know off the top of your head that it's like
I think I was right.
So here again, this what I'm taking the limit of is an inverse trig function, right? That's going to be outputting me an angle in radians.
Yeah.
What are radian angles measured in most commonly? Terms of pi. I see 1.5, that's about half of 3.
that's
Probably pi/2 would be where my head goes. Now that you've seen it, when you do a limit for like one of these inverse trig functions, you're going to be thinking, oh, I'm looking for something in terms of pi. So it becomes a lot easier to look at that number and go, oh, probably pi/2. Anybody have a guess as to what happens if we go to positive infinity?
pi/2.
Yeah, probably positive pi/2. Let's go ahead and just jump to the chase there. Looks pretty good.
I could really think about that. I was all looking around right now.
All right.
I have a question.
Yeah, what's up?
So the reason we did like the 100, 1000 was like what was wrong with the graph?
So if you were looking at the graph, this doesn't look like it's coming to an integer. It's just coming to some number between 1 and 2,
Oh.
right? And down here, it's just some number between -1 and -2. I can't really read what that number is from the picture.
Okay.
So that's why I went to the table.
Okay. When you put it on like the trig on the graph, is it counting by half pi?
So the x-axis, every tick mark is a half a pi,
Okay.
but the y-coordinates are just 1, 2, 3, 4.
Okay. Yeah. I understand. Okay.
So I did the zoom trig. I probably shouldn't have bothered to do that since the inputs were radians and the outputs, or the inputs are numbers and the outputs are radians. I probably should have just left it the way it was, but
Okay.
you know, you live and you learn, right? Okay. So here's some function f of x that I've defined with this graph. So let's figure out all the limits that are infinite here. All right. Shrink that down so we can see everything at once. All right, what's the limit as x approaches negative infinity of f of x? Looks like 2, right? You're looking at this end of the graph, which looks like it's following 2. How about as x approaches positive infinity?
Said you have to sign it, but I don't know if you want it or not.
Here.
Oh. Not you, she did. Okay.
There's my signature, too.
That's your signature. Can I just throw it out?
Yeah, I think you can.
Okay.
I would treasure
No,
that.
she's like, just sign it. I was gonna
Yeah,
throw it
hang it
out.
off. That's something you frame, not throw out.
It's okay, man. It's no big deal. I trust you.
Yeah.
You should frame it in this class, you know, put your signature on the wall.
All right. The limit as x approaches negative 1 from the left is positive infinity. How about from the right? It's also positive infinity, right?
Oh, right, yeah.
You're looking at the next one probably, right?
Yes.
How about positive 2 from the left? Negative infinity. And positive 2 from the right? Positive infinity.
Yeah, these are identical.
This feels okay?
Are we gonna need to write out like all the limits?
I know.
Depends on the question, right? So this is a vertical asymptote. This is a vertical asymptote. That's a horizontal asymptote. And that's a horizontal asymptote.
Nice.
So the way we defined vertical asymptotes was if you have a limit, a one-sided limit that goes to either positive infinity or negative infinity, that constituted a vertical asymptote. That's what we saw in the right circles on that in red. And then our new definition for a horizontal asymptote, if you have either end that goes to infinity and settles down to a specific value, those are horizontal asymptotes. So I'm just using our two definitions that we've had of asymptotes previously to do that.
Oh, is that IP? What is that IPT? Like VA, and
HA.
Horizontal asymptote.
Okay. Next is a real helpful theorem. And this theorem that I'm about to give you is going to be, well, I don't know about life-changing, but quite useful in avoiding some of those indeterminate forms. So if r is greater than 0 and a rational number, then the limit as x approaches positive or negative infinity of 1 over x to the r is 0. Let's show you where this is going to become useful. So let's say we want to do this limit. If I try to do direct substitution, I'm going to end up with infinity over infinity, right? That's not helpful. So what am I going to do here? I'm going to multiply both the top and bottom by the largest degree variable in either the numerator or denominator. In this case, that's an x squared. When I do that, I'm going to get 3 minus 1 over x minus 2 over x squared. And I'll get 5 plus 1 over x plus 1 over x squared. Oh, that should be a 4 there. Yeah, sure. Then using my limit rules, I can just kind of distribute that limit all throughout. So it's the limit as x approaches 3, or the limit as x approaches infinity of 3. Just 3. Everybody agree? Limit of a constant is always a constant. Using theorem that we just gave you, the limit as x approaches infinity of 1 over x is 0. And the limit as x approaches infinity of 2 over x squared is just 0. And the limit as x approaches infinity of 5 is 5. The limit as x approaches infinity of 4 over x is 0. Then the limit as x approaches infinity of 1 over x squared is, so it just turns into 3/5. Woo! Okay, here. You like that? Then do this. Are you happy now? Okay. Sure. She was complaining because in the theorem it was a 1 over x to the r, and in some of those I had like 2 over x to the r or 4 over x to the r. And I said, okay, well just think about it this way, and I used the limit rule to pull the constant out front of the limit. So I have 2 times 1 over, which again, 2 times 0, so still 0, right? That's fine.
And then you pulled out the,
I did the same thing with the 4.
the 4 was, how was it written before?
4 over x.
Yeah, I wrote it as 4 over x, and then
Got rid of the 4.
people were complaining, so I wrote the 4 as a coefficient. You know, hey, you don't have to G's me up. It's not just me up.
Well, I like to go like I got
All right. All right, one more example, and we'll stop here.
Yeah. Oh, I see.
Oh, yeah.
Right.
That's not what I want. That's the same
Are we
thing.
homework quizzing on tomorrow?
That
I didn't know how,
I'll study on the weekend.
okay. You want to talk about this now? We can talk about this now. So the format I was planning on giving for the homework quiz was going to be AP multiple choice questions that are banded. The scoring was going to be banded the same way it was for the homework. So like 8 or more was a 10, right? So you have a lot of wiggle room there. It was going to be multiple choice, just like the other practice one that we had done
Like in class.
in class. I mean, if you want to do that, I'm going to tighten the bands then. So like it's going to take more right to get a 10 if you want to have a partner.
Wait, is it on the computer?
Yeah, you'll do it on the computer.
What section is it on?
I would say it was up through like 2-3.
Oh, sweet. Okay. All right. So yeah, 2 classes.
Oh no, what are we doing? I can't remember. Let me look again.
We're on 2.5 right now. We just finished 2.5.
Continuity definitely is in there.
So maybe the partner's the way to go.
How many
I'm gonna study tonight. I gotta know what we're gonna do.
So I would say if you wanted to use a partner, your bands just go down to like by 1. So everything just shifts up 1. So instead of like 8 to 10 being a 10, it's 9 to 10.
I'm not. You guys are interested in part.
And that kind of follows its way through. I can't hear you. 6th hour is the lunch divider on the X day. I have first lunch, so you know what? I'll let you. If you work by yourself, you get a wider band to get high score. If you want to work with a partner, that's fine, but the band's narrow a little bit, which I think is probably fair, right? And I'll let you know what the bands are again tomorrow.
Thursday and Friday.